Hi, my name is Andrew Greaves. I'm an enterprise cloud architect from UC San Diego Health, and I'm here to talk to you about some of the things we've done at UC San Diego Health, including a chest X-ray AI for early COVID detection, some other research enablement for our organization as well. So I've been at UCSD for over 20 years in a variety of capacities, from Director of Biomedical Informatics, Director of IT for the UCSD Cancer Center, and now I'm the Enterprise Cloud Architect. So UCSD at a glance, we have over 800 beds in 2 different medical centers and a bunch of various clinics across San Diego County with over 800,000 outpatient visits per year and close to 80,000 ED visits, annual admissions around 31,000. And a very large research portfolio of around $400 million in NIH funding. And you can see the rankings that UCSD is proud of. So the first topic I want to talk about is a sepsis machine learning pipeline that we helped build, and our focus on sepsis is because it's the 3rd leading death in the United States alone, affecting over 250,000 Americans each year. The benefits of sepsis detection and early sepsis detection, obviously, decreased mortality for patients, the long-term deleterious effects of sepsis can be very impactful. So, anything we can do to reduce or remove those long-term impacts greatly impact our patients' outcome and clearly their satisfaction. So one of the things we worked with was a sepsis prediction in the sepsis prediction pipeline. We worked with the Department of Biomedical Informatics, the Director of Predictive Analytics, a professor named Shamim Namadi, who came up with a sepsis prediction algorithm that was able to ingest massive amounts of data in a very short time. So we worked with Dr. Damati to develop a very high input early sepsis prediction platform, taking in data from Philips monitors, which receive and send data every 3 seconds to the pipeline. So those are things like pulse ox, respiration rate, heart rate. And the reason it was important to get it from the Philips PixIX system and those monitoring systems was because of that frequency. Normally what's recorded in Epic is recorded every about 15 minutes as nurses certify that information going into Epic is correct. So getting this every 3 seconds allows us to do very early detection. So as you can see from the diagram up top, we have the PixIX machines feeding into this SmartLinks pipeline, and SmartLinks allows us to ingest the data and then filter the data appropriately. We're shipping it then to this Mirth Connect interface, which ingests information from our CorePoint interface from Epic, which is not only stores our ADT, which is admissions, discharge, and transfers, but also lab information and other vitals that are shipped to the Mirth Connect, and then those are then forwarded into this clinical decision support account where we have this pipeline running. So that allows for very early detection of specific variables or data elements that allow for feedback to clinicians to evaluate patients in ICUs and critical care facilities. So the next pipeline that I want to talk to you about, or architecture that I want to talk to you about, is our COVID imaging analysis pipeline, which is really a pneumonia detection pipeline that allows for non-radiologists to have a very easy way of detecting pneumonia on frontal chest X-rays. So as you can see at the top, I'm obviously not a radiologist. As I said before, I'm a cloud architect. I wouldn't have much of an idea of what was going on here, though. Obviously this area where the lungs are look odd. What this imaging pipeline allows us to do is produce this secondary image, which is kind of a heat map of suspect areas that are specifically suspect for pneumonia. The reason this was important at the timeline that we put it in place with COVID was that testing availability was very sparse. And so we had to be able to prioritize patients in some logical fashion. And given the symptoms of COVID, one of the best ways to do that was to detect high-risk patients by pneumonia detection. So the Department of Radiology, Albert Sau, approached us about an algorithm that they had, which is this pneumonia detection pipeline or pneumonia detection algorithm. And what we're doing in the architecture diagram here is we're taking from our on-prem organization, our AGFA Impacts, which is a PAC system, picture archive of all images that come out of our health system. So here you see the sick patient, they get an X-ray. That image, if it's a frontal X-ray, gets shipped down to this pipeline and this Ombra gateway. The Ombra gateway takes that information or that image set and drops it into object storage in S3. And then we have events triggered that create an SQS messaging queue. That messaging queue allows for our pipeline or our Docker container here to pick those up and drop those images into one of the containers that we have spun up that does this particular analysis. So ultimately, that analysis running on these containers is running in Python, generates these secondary images in about between 12 and 15 seconds. And then the secondary image is put in an outgoing bucket that Ombra picks back up, sends back into the AGFA Impacts. And then what is displayed in the EHR is a side-by-side comparison. So, for the radiologist, who this would be easy to detect, they also have kind of this secondary AI as a guide. And then for non-radiologists, because one of our concerns was that, if our Department of Radiology was impacted greatly by COVID, we may need to have other people be able to make these primary reads fairly quickly so that we could escalate at-risk patients. And that is ultimately the pipeline. We were able to set this up with Amazon's help in less than 7 days from the first time the proposal came kind of to my desk. We worked with Expertech Solutions, one of our third-party Amazon consultants, and the Department of Radiology. And like I said, 7 days was pretty impressive. We're now making modifications to the pipeline. We're making it more robust, scalable, using things like we're moving from just EC2 with Docker running to ECS. And then we're actually looking at these gateway pieces and removing them and using AWS transfer to just FTP the images directly into S3. But more to come on that. And then the last piece with this is that as we start to look at model drift, shift, and retraining the model as we have more data in it, we are actively exploring AWS SageMaker, which, if you haven't used it, is a fantastic AI and machine learning platform. So the next thing I want to talk to you about is the creation of a virtual research desktop. So we have a lot of researchers, we have a lot of big protected health information payload data sets that are available in our environment. And traditionally, we've been sending them out to people's thumb drives or to local managed and non-managed machines, and that creates what we like to call a nomadic data set, which is not something that compliance, regulatory, and security is very happy with. So we worked with Amazon very early on and our Altman Clinical and Translational Research Institute here at San Diego to create, using workspaces, this virtual research desktop. So the architecture diagram just shows at a high level our ability to use AD connector, create AD authenticated with Duo MFA, Amazon workspaces that allow users into our environment and provide them access to data sets. So some of this is happening, in RDS, some of it's happening in local data sets that we are dropping directly onto the workspaces. One of the advantages with the workspace is that we can configure the environment. So what I'm going to show you here on the left is, the kind of customer side experience. So they log into the workspace client. It's a lot like a Citrix type environment where there's a local client. That brings the user, once authenticated, into the desktop. So this is the desktop set up with all the research tools that have been requested. We create kind of a baseline image depending on the type of research that our researchers are doing. Obviously, the tools that they need are a little bit different, but as a baseline, we have things like SPSS, SAS, JUMP, R, Navicat for getting access into different SQL environments, ArcGIS for mapping GIS environments, Minitab for analysis. So once in the environment, we are actually providing a FSX Windows file share that securely groups them into, they have a user folder as well as a user share. So if they're collaborating with multiple institutional partners, we have shared directories that allow them to share data across, but then also keep their own data private to their specific private volume. And this is just an example of connecting to one of our RDS instances. We run a variety of commonly shared databases that I'll explain on the next slide that allow for users to get access to large data sets that are commonly shared. And usually what's happening with a lot of those data sets is they're distributed all across campus, but we're centralizing that. And number one, from a security and efficiency standpoint, it gives us a single point of entry. It gives us also the control to provision users who have gone through the proper authorizations to get access to data sets. So I mentioned the data commons. So this is kind of an expanded view of how we're using the AWS workspaces. This involves not only our Altman Clinical and Translational Research Institute, but also our Department of Biomedical Informatics. And so we have two different pathways that I'm showing here. One is these workspaces that live in our management account, where we're using these as administrative bastions or jump hosts. Kind of into the environment allows us to provide kind of a controlled environment where people can store like their access keys, passwords into infrastructure that they are authorized to use, to modify, to manage. And then we also have these workspaces that we would call the VRD that live in the CTRI account, where these are users who are getting access into applications and/or data sets. So in this Health Sciences Information Services account, we are actually hosting data sets, things like the MIMIC data set, which is a data set that is critical care data from Beth Israel Deaconess that's all de-identified. It's about 11 years of data, but it's a fantastic resource for researchers to get in, kind of dig in to look at their hypotheses and see based on this historical data set if some of these things apply. We're also providing COVID data sets from our organization as well as across the UCs. There is a COVID research, a de-identified research registry that combines the power of all 5 of the University of California's into a single data set. And then we also have things like TCGA that we are, that's a genomics data set of about 11,000 different cases specifically targeted around cancer. So depending on the research people are trying to do, availability of the data sets in kind of the traditional database format. And then we're also allowing users into our data lake environment that we're rapidly expanding, because it's a lot less expensive to use things like storing data in S3 using glue crawlers to kind of catalog that data, and then use Athena and QuickSight to produce some very quick visualizations. And then the next slide, what I'm going to talk about is what we're doing specifically with the Department of Biomedical Informatics around a translational research portal and access to other data sets for less technical users. So, using Athena and using QuickSight or even, SQL provide some technical hurdles for some of our researchers, specifically around, our clinical researchers sometimes aren't the most technically deep. So providing other avenues for them to access data and explore it that doesn't require the technical depth is mission critical to our overall facilitation of research. So this is kind of a mock-up of what our translational research portal looks like. This is an actual screenshot from our virtual research desktop where we've worked with a company called Tag Bio to develop this translational research portal. So what Tag Bio allows us to do is take a lot of these variable data sets and create this kind of notion of a data node. And then it allows through a very user-friendly interface researchers access into different data sets. So what you're seeing here is access to different data sets that people have role-based access to once it's certified that they are regulatory-wise allowed to have access to the data sets. We control that through the application itself. So and really kind of the overall process here is, we bring in data sources, they're integrated into these data nodes. So depending on the type of data, those become the actual nodes. The application through the UI allows for, variable analytics. You can examine data quality, DNA mutations, variations, cutoff expression. You can do Cox analysis, etc. But the kind of meat and potatoes of all of this is that once you have the nodes built, you can build kind of this data mesh that flows across all of the different data sets and allows for some very powerful analysis that wasn't previously possible, and in particular for those users that aren't particularly data savvy or technically savvy. So what I'm going to show you here is access to one of these data sets. How a user uses this data set. So I log into the translational research portal, and I'm interested in exploring the COVID-19 positive patients. We build protocols in here that are stored just like a stored procedure for SQL. You can see what it's comprised of, what the analysis variables are based on, and then you can run the particular protocol. You can modify this protocol. But the neat part about this is then I can share it with other researchers in the translational research portal that have authorization to also explore these data sets. So you can see down below how you can actually analyze and change variables. It's very flexible and it's very user-friendly. I just want to acknowledge all of our collaborators at UC San Diego Health, specifically in information services, Dr. Chris Longhurst, our CIO, Dr. Mike Hogarth, our clinical research information officer, John Torello, our chief technical officer, Derek Dutt, Mark Silvestrak, Ken Waukee, and the entire IS security team. Our collaborators at the Altman Clinical and Translational Research Institute, the director, Dr. Gary Firestein, Win Tru, Tony Chen, and Perry Shipman. Department of Biomedical Informatics, Dr. Lucilla Ona Machado is the chair, Paulina Paul, Tyler Bath, Kai Post, Ji-Hoon Kim, and Nancy Erbst. I would not be here and not be nearly as successful if it wasn't for our collaboration with our AWS partner, Expertech Solutions, Chit Bhattacharya, Dev Bhattacharya, and Justine Giger. Tag Bio has provided enormous resources to us at no cost at this point as we start to build out this portal in response to our building out of the COVID registries. So Tom Covington, Jesse Peckerton, Mark Mooney, Ken Broadhagen, and Wade Webster And certainly we would not have made it nearly as far, nearly as quickly without the help of all of our AWS partners. So Dr. Prathma Srinivas, Daniel Hilt, Heather Madsen, Randy Ridgely, Guy Eldridge, Andrew Defoe, and many others. And I really do want to say a special thank you to AWS for the Diagnostic Development Initiative that has been instrumental in helping us provide the infrastructure to our researchers to do the work that they are so passionate about. And if you have any questions, feel free to contact myself, Jit Bhattacharya, or Mark Mooney from TagBio. Thank you very much.